Hello and welcome. Today we get to talk about a great subject, space. Everybody loves to talk about space. Our presentation today is called The Right Stuff for Really Remote Edge Computing. It features Mark Gamble, Senior Director of Product Marketing, and a special guest, Wayne Carter, VP of Engineering. Wayne is responsible for leading the vision, strategy, and development of Couchbase mobile, IoT, and edge computing. And a couple housekeeping items before we turn it over to Mark and Wayne. Please feel free to use the chat function and get to know your fellow attendees. And use the Q&A. We'll keep Q&A to the end of the presentation, but if a question comes up during the presentation, feel free to type it in. Don't wait until the last minute and get your questions in there for Mark and for Wayne. And then also a reminder to check out the docs section. There's some great follow-up assets on there. You can kind of take a look at the deck. You can look at Couchbase app services, a blog that we've recently done on this similar subject. So feel free to use the docs section and get some more information that way. And with that, I will turn it over to Mark Gamble.
Great. Thanks, Suzanne. Hi, everybody. As Suzanne said, Mark here from Couchbase. Super excited also to talk about today's topic on edge computing. And in this case, we're focusing on how edge computing architectures, appropriately applied, enable highly resilient and fast applications that work everywhere, all the time, regardless of internet connectivity. And joining us for today's presentation, of course, Wayne Carter, VP of Engineering here at Couchbase, heading up, as Suzanne said, our mobile and edge product line. And Wayne is as knowledgeable as it gets, really, on all aspects of edge computing for mobile and IoT applications. And as such, he's the perfect subject matter expert for today's topic. So Wayne, thanks so much for joining us today.
Thanks, Mark. It's great to be here. It's an exciting space. It's evolving fast, and really interested in sharing how the capabilities of edge computing can help, and the unique capabilities and where it can help in really remote locations.
Got it. Yeah, agreed, 100%. And we have a lot of ground to cover, and we'll try and do it in just the shortest amount of time possible. So let's go ahead and dive right on in. We're going to focus today on three main areas. First, we'll cover the need for edge computing. And this encompasses, of course, what it is, what it enables, why it's necessary, and specifically where Couchbase fits. And then we'll get to the really fun part where some of the spacey stuff comes in, as Suzanne talked about. Wayne's going to circle back and talk about the ASC stack for edge architectures, and that is AWS, SpaceX, and Couchbase. And then finally, Wayne will also cover results from tests with AWS Snowball, Starlink, and Capella, testing for latency and bandwidth efficiency. So make sure to stick around for the entire presentation because the results are just really phenomenal and eye-opening. So I'll begin by setting the stage for edge computing. What are the challenges that would drive an organization to seek capabilities for running applications at the edge? So we'll do this by taking a look at just three examples here. So first, let's consider an offshore oil drilling platform in the North Sea. And let's say that there's, as usual, about 3 or 4 control room operators continuously monitoring and being fed data from thousands of sensors around the platform, from downhole, subsea, topside equipment. Operators have to monitor and control a multitude of variables and each have different settings. And at the same time, have to also consider things like wave height and temperature and humidity, all of these things that can impact production. And there's so much information coming so fast that operators, this is a true thing that a McKinsey study found, they slow down production to reduce risks and hazards. So, this deluge of data becomes a barrier to efficiency that companies, oil and gas companies, just can't overcome, especially when their on-platform applications require data processing in the cloud. So suppose you need to analyze critical warning data from a pressure sensor on the platform. And if that data has to be processed in the cloud data centers, it has to travel incredible distances at great expense over unreliable networks. And this incurs, high degrees of latency or network slowness. That's what that equates to. And so by the time a result is actually sent back to the platform, it could be just too late to take any action. So what's needed is a way to keep up with the challenge of this deluge of data happening at all times on the platform without relying on the internet. So continuing kind of on the problem side of things, next let's consider an airline. In travel, great customer experience is the best competitive advantage in a packed market. And the means of providing a personalized experience for passengers, that this basically means that you should provide a personalized experience as well as make onboard processes as fast and efficient as possible. So to do so, it's really imperative that cabin crews have fingertip access to information on each and every passenger, and that they always know current inventories for meals and amenities and duty-free items so that orders can be fulfilled immediately and no one buys a sold-out item. But if the data that holds this information is in the cloud, this becomes a barrier when in flight. How can an airliner provide the personal experience for passengers without reliable network access? So what's needed here is a way to access passenger data and inventory data instantly without relying on the internet. So thirdly, let's consider a cruise line that wants to enable hyper-targeted marketing through on-vessel applications. Making recommendations and offers to guests in real time that lead to upsell, such as offering a 20% off coupon for a bottle of wine that they see I order every evening with dinner. This concept relies on the ability to capture guest data at all times, to know where they are, what they purchase, when they go to specific places. All the things that build a better guest profile and allow for this kind of personalized service. The problem is the guests are all at sea, where the internet is slow and unreliable, and they're all moving around the ship, which is moving around the ocean. And this makes it a challenge to capture and react to their activity with the onboard apps, mainly because of cloud data center dependencies, right? What's needed is a way to process and react to changes in guest data in real time without relying on internet connectivity. So some common themes here, and these use cases represent a growing class of applications that require 100% uptime and real-time speed guaranteed, regardless of internet connectivity. And edge computing is the answer, right? The goal of edge computing is to bring data and compute closer to the applications that consume it. And to do so, you need to embed a database to edge clients, reducing dependencies on the internet, and you need to sync data from the edge to the cloud for data consistency and integrity. And this model serves to speed up applications because data doesn't have to travel all the way to the cloud and back. And it makes apps more reliable because local data processing removes internet slowness and outages from the equation. And it handles privacy better because sensitive data never has to leave the edge. And lastly, it promises more efficient bandwidth usage by lessening that load between the cloud and the edge, which is really important when on shared networks where bandwidth can vary greatly depending on time of day and demand. So it's really one thing for me to describe an edge architecture, but Wayne, I'm going to bring you into the conversation here. Can you dig in a bit deeper to how edge computing gets around these challenges of cloud computing for uptime and speed in applications?
Yeah, so let's look at what edge computing is by contrasting it to cloud computing, right? So the whole idea of edge computing is to make systems faster, more reliable, enabling employees and partners to do their jobs and interact with customers and each other where they otherwise would not be able to, enabling customers to have a much better and faster experience when using the digital technologies that underpin the business. Right, we're all going through digital transformation, and we have these multiple choices on how we actually do that. And when you talk about business critical processes, maximizing availability, maximizing speed, maximizing privacy, and reducing the overall cost of the system is a really big challenge and something that edge computing can help with. So if we start with a cloud computing architecture, so a lot of this, many of you may already understand, but just to level set on the conversation is what exactly are we testing and how are these results being achieved? So let's start with cloud computing. You have your database, your data systems, and your web services and applications deployed in the cloud. And those are being accessed from a client, right? So that could be a mobile phone, it could be a tablet, it could be a web browser, it could be a desktop, it could even be an embedded system. The key thing about cloud computing is your computing and your data is in a centralized cloud location. So now let's compare that to an edge computing system, and we'll build it up from here. So with edge computing, you're going to add additional layers in the stack that allow you to place and access compute and storage closer to your point of interaction. So starting off, and this is going to build out into a much larger edge computing topology, but just to start out, okay, so we add an edge location. In this case, it's being imagined as the cloud is in the west. So this could be a region in one of your favorite cloud service providers. Then we have another data center down at the edge, and this one's imagining you're in San Francisco. And then we have a client that's also running in San Francisco. And then the edge and the client location have additional networking layers, which allow this additional communication paths for these different parts of the system. So as we build this out more, we add our web services that we want near the edge, right? You don't always put all of your web services and data near the edge. But we're going to put our web services and our web applications and our data that we want accessible in San Francisco into the San Francisco area. And now we're going to start rerouting our application. So when a client is accessing from San Francisco, we want that client to access the San Francisco data center. And so there's a mobile device here accessing those services while the device is physically in San Francisco. And once we have the San Francisco edge location set up, we now need consistency between our data. Our web services are the same, right? The logic, our compute is the same in these services, but the data is changing and needs to be moved down to San Francisco. As it changes in the cloud, move it down to San Francisco, that data that matters. And then as data changes in San Francisco, move it to the cloud. And now let's make this a little more complicated. Let's actually span different areas of the US. So we'll pull up additional cloud and edge and client locations in the east. And then we'll add our web services and databases and clients into those areas also. And then we'll connect our east and west. And now we have, this is getting even more complicated here in a second, but now we have a full edge system that spans multiple regions in the US and multiple cities, metropolitan areas that can serve the devices accessing those metropolitan areas faster and more reliably. So now let's add a metropolitan area that doesn't have a local edge data center. What happens there? We've decided that this system should have edge data centers in San Francisco and New York, but LA, what happens when a device connects in Los Angeles? So what they'll do is they'll connect to the cloud, the closest cloud, and they won't have the same speeds and same reliabilities, but they will have access to the services at the cloud speeds. Now let's add an additional couple of devices in LA. Is there a way that we can use edge computing to speed up the communication between these other devices, even though I don't have an edge data center? So let's add a few databases in the client. So what this is doing, so before we had all of our edge clients were just accessing the edge data center or the cloud data center using connected technology, so REST. And now we're going to actually take advantage of the client tier for really edge computing. So the closest you can get to interaction in an edge computing topology is on the device itself. And so that's what those databases represent in the databases in San Francisco, LA, and New York City. And so those databases sync with the cloud, which means that the data will be consistent, right? So as data changes on the device, it syncs with the cloud. I'm looking specifically at LA here, but it also applies to New York City and San Francisco. And then as the data changes in the West, it transfers down to the devices. That means the devices actually now gain the speed of edge computing. The devices with the database in it don't have the latencies and reliability issues you might have when accessing the cloud. They have the data locally on the device. So they now are going to get the higher speeds associated with local access. And that's a big move in edge computing. It's actually one of the most popular moves in edge computing. And then the additional one we're adding here is that, okay, I want these devices to be able to communicate with each other when they don't have a shared internet connection or a shared internet endpoint. Well, how can I do that? Well, edge computing enables additional networking layers also. So in this case in LA, those devices are communicating over a private area network. So that can be a shared area network, a shared network that they're running on that's actually a private area network, or local area network, or they could have direct peer-to-peer networks via Wi-Fi, Bluetooth, or a number of other technologies. And so when those devices, you can imagine that in like an airline case where devices are moving around on the employees' phones in the aircraft, and as they take orders on the plane, they're going to share those orders with the other employees on the plane, and they're going to do that via either a shared LAN that doesn't have an internet connection, or they're going to create ad hoc network between the devices. All right, and so this just kind of summarizes what I've been talking about so far. So you have Couchbase technologies. One second, my headset fell out. So where does Couchbase fit into this stack? So you need databases that can run in the cloud, run at the edge, and run on device. And Couchbase has database and sync technology for all of that. So in addition to databases, you also need sync, and that's what's going to give you the consistency between databases. And so for the server, we have our distributed database server that runs in the cloud, the same thing for the edge, and then we have our embedded NoSQL database for devices, whether that's phone, tablets, desktops, embedded systems, IoT. We have a great selection of supported platforms.
Great. Thanks, Wayne. I think that really helps illustrate, especially the differences in edge computing from cloud computing. What's most noteworthy is that edge computing, the concept, doesn't replace cloud computing. It's about extending the cloud to the edge. And so having the right database technology to help make this a possibility is really key. So what we wanted to do now was talk about the Couchbase product stack that enables edge computing architectures. So this is the Couchbase mobile product stack. It's the foundation of our support for edge. So on the left, we have Couchbase Server. This is our flagship modern database server with support for SQL, analytics, full text search, and eventing. And then on the right, we have Couchbase Lite. This is the embeddable version of Couchbase for mobile, IoT, and custom embedded devices. So Sync Gateway sits between and is responsible for secure data synchronization, routing, and access control between the edge and mobile clients and the server tiers. So, these are the fundamental components that can be layered on top of each other across even those complex topologies like Wayne was just talking about. So on deployment, these capabilities can be deployed two ways. Fully managed with Couchbase Capella and Couchbase Capella app services, or self-managed, where customers install Couchbase themselves on public or private clouds, on a cloud edge service, or on-prem, and or any combination of the same. So again, our unique capabilities here are to be able to knit these together into multi-layer edge topologies. So in fact, let's take a look at, kind of simplified version of topologies. So Capella is available on AWS, GCP, and Azure, and it provides a hosted and managed database as a service, which runs Couchbase Server under the hood. It also provides fully hosted and managed app services, which run Sync Gateway under the hood. Common topologies for app services applications include offline first sync. And this is where applications can work in isolation for extended periods of time using Couchbase Lite for embedded data processing. And when connectivity does become available, they use app services for secure and highly compressed, efficient data synchronization over the WebSockets-based protocol that we provide. Another common topology is peer-to-peer with Cloud Sync. So this is where Couchbase Lite is deployed on edge devices, and to facilitate collaboration without a centralized cloud control point, the peer-to-peer sync functionality of Couchbase Lite is used to sync data between the edge devices when disconnected from the internet. And Wayne talked about an airline example where cabin crew can actually work and collaborate and update data between devices using this kind of this feature without the need for a central internet control point. And lastly, app services can also support mobile and web apps with secure access to Capella via REST calls. And in this topology, clients can either embed Couchbase Lite or call the REST API directly from web or desktop applications. So kind of with this background on edge computing and Couchbase capabilities and where they fit, now let's turn to a practical application of an edge architecture. And Wayne, recently you and your team decided to see if you could solve those challenges that we opened up the presentation with by conducting some fascinating tests using Couchbase with AWS and Starlink. So can you tell us a little bit about that effort?
Yeah, so the focus of this was really remote locations, right? So the key components you need when building a edge computing architecture is you need a cloud compute environment, you need an edge compute environment. That's where your services are going to run, right? You're going to run logic, web services, web apps, right? You need a network connecting your cloud and edge, and then you need a database that can be deployed in each layer that can then also sync. Right, the sync component is a very important part of that. It plays a very big role. And when we went to choose this, right, it was the key of really remote locations. So we needed to choose these, right? So for the edge side, we use AWS Snowball, right? What we were looking for also is what you can get, the system components that you can get off the shelf. What can I order and have delivered to me in days and weeks? Right, where I'm able to then build my system on top of that. So we chose AWS Snowball. The Snow family is awesome. There are other types of environments that you can choose, but we went with the Snowball. It's bigger and beefier, and really a great example of the level of compute you can actually get at the edge. It doesn't have to be small. Right, you can actually have large amounts of compute and storage at the edge where you can get a lot done. Then for the network connectivity, it was to that really remote location concept that we were looking at here. And so we chose Starlink. And then for running in the cloud, we chose Capella for our hosted database and services solution, running in an AWS region. And so let's look at the test scenario, and then I'll actually show the architecture of the test setup. So when we ran this test, we were looking to measure the performance of the system, right? So we didn't look at availability, for example, which is another big component, or privacy, which is a big component of edge computing. What we wanted to look at is how can we make this system perform better? So we looked at response times when I'm accessing the system and interacting with it. How fast can it possibly be? And then how much data is it using? How much is the system going to cost me to run? And then we backed all of that with database technology from Couchbase, and then deployed onto AWS regions. So that's our compute location and the AWS Snowball. And then for our client, I'll just touch on that so I didn't touch before, is we use a MacBook Pro. So we're looking to use a standard device that you might see in a real world case. And so the architecture, we actually used a number of different ways to deploy this. So on the cloud side, we use Couchbase Capella. So Mark covered that that's our fully hosted version of our product, right? And we deployed that in AWS, and then including our DBaaS database with app services on top of that. And those app services expose a secure API that we use. So we use the REST API in this case. We weren't using the sync API. We use sync to sync between the Capella and Snowball, right? But when I run the test, when I talk to you about the tests, we have a set of tests that do REST against the Capella app services, and then we have a set of tests that run against the gateway REST services. Those are the same, right? App services is hosted gateway at the edge, and Couchbase server deployed at the edge. All right, so the first test was to write 1,000 docs. So the documents that we used was a product catalog case, right? And we were using about 1K of data. It was a little bit varied, but about 1K compressible data, things that you would normally see in just a product catalog, right? And we wrote 1,000 new documents. We started with a clean database, write 1,000 product catalog items into the Snowball over to wired LAN, and measure the amount of data transferred and the speed per operation, right? So how much did I transfer and how long did it take for me to get a response from the beginning of the test? Test 2 was to sync those 1,000 new documents from the Snowball to Capella over Starlink and measure the amount of data transferred and the complete amount of time to transfer. So I wrote to the edge, and now I'm going to sync that to the cloud. How much data gets transferred? That's an important question. Right? How much data gets transferred when I write the documents, and then how much data is transferred when I sync from the edge to the cloud, and then how much time did it take to sync? Test 3 was to do that with the cloud and sync to the edge. So write 1,000 new documents. So we wiped out the environment, started with a clean environment, write 1,000 new docs to Capella over Starlink. That means make a direct REST connection, writing 1,000 requests to Capella that are going to be stored in the cloud, right? And we measure the amount of data transferred and the speed per operation. And then in test 4, we reversed the synchronization, right? Sync from the cloud to the edge, syncing those 1,000 new docs from Capella to the Snowball over Starlink, measuring the amount of data transferred and the time to complete. So we have all of the I/O and the speed, the amount we were actually writing, the amount we were actually reading, and the amount of time it took in each of these operations. All right, so latency is dramatically reduced. This is a common theme throughout edge computing, right? So this is a locale problem. So the fact that the compute is in closer proximity to the point of interaction means it's going to be faster to access, right? So if you look at the distance between these, right, you're talking about feet of distance or tens of feet of distance at the edge environment from the actual system you're interacting with, the Snowball, right? Bringing data to the device, the laptop, the MacBook Pro, right? And the write speeds of that were 10 milliseconds at the edge, with cloud being 440 milliseconds. So approaching, I mean, 98% is a massive reduction in speed. And if you actually look at like what are the capabilities, why is it so much further? Well, the orbital altitude of a Starlink satellite is 340 miles. That's about the distance between San Francisco SFO and LAX. And you not only need to communicate to the satellite, but you also need to communicate down again. So your communication is traveling about 700 miles compared to a few feet or a few meters that you have when accessing it locally. And then reads were similarly improved, right? There's very little difference between, it's really just your time for reading and writing the time for writing, that's the difference in these speeds. So 98% reduction in any type of read-write activity that you need to perform when you're writing at the edge as compared to writing at the cloud. And then there's the reduction, I pointed this out as I talked about the setup of the test, is how much data is transferred when I write to the edge, so the network connection between my MacBook Pro and my Snowball, how much data was transferred over that connection when I wrote the 1,000 product catalog items? And then how much was transferred when I synced it to the cloud, right? And there's a big difference between those. When we write from the MacBook Pro to the Snowball, writing over the gateway REST interface, we're doing run length compression, right? There is compression involved between the device and the gateway, And it, typically you're going to get about 30% compression, something like that. It depends on your data set, but 30% is typical run length. And then, but when we sync to the cloud, we get that run length compression, but we don't get it for a single doc, right? Like if we write a product catalog doc, we get to compress, the things that are duplicated within that one record, right? And there's not a ton, there is some duplication, but there's not a ton of duplication. When you sync, you actually get to do a lot more optimization for the data you transfer over the cloud network connection, right? So the Starlink in this case. It's important to conserve that. That's a shared network. That's a shared network resource. So the use of the network by others is going to impact the same people in the same cell or other people in the same cell. And so with that, we can do run length compression across documents, which you're going to have heavy duplication across documents. Like every field is going to be named the same, right? Product catalogs have prices, descriptions, names, right? And the actual key fields and many of the other components are going to be duplicated. And even for enum values within the records themselves will be duplicated across documents. So we get this massive additional compression because we get to be smarter about what we compress and make choices about how we compress across records instead of just a single request to the web service. And this number, 42%, will, if you think about it, is actually maybe the next slide is a better one for me to point through the details of this. Is kind of like focus in on these points of measurement that we made. So I covered kind of a bit about the speed, right? Things that are closer or faster, right? Like massively faster. And then with data compression, I'm pointing out the fact that we have a lot more control over how data is transferred to the cloud. So we get cross-record compression that I just kind of walked through, right? But we also get delta compression. So when you mutate, we can actually just take the part that you change. When you change like a price, for example, on a product catalog item, don't transfer the whole record, just transfer the little bit that was the price. So we get to do that because we can coordinate between the cloud system and the edge system. Right? They can ask you, the edge system can say to the cloud system, what version do you have? And he says, I have version 3, and the edge system, oh, you need to go to version 5. Let me give you a patch between version 3 and version 5. Simplified explanation of what I'm talking about. And then we have lots of other capabilities, right? We can delay transfer so that we can batch and compress across those batches. We can do filtering, so you're only moving data that you actually need to move to the cloud or from the cloud to the edge. So you have this ability to sync and be smart about how the data transfers has massive implications on the cost of the system when you're talking about the data transferred between the ingress and egress in and out of these layers of the network. All right, and so just, I talked, this is kind of a generic use case. How do you move product catalog around? But there's tons of use cases where this apply, right? And Mark will actually walk us through a few of those now.
Thanks, Wayne. It's just so fascinating that, simple concepts that make complete sense and you really help take a lot of the complexity out of edge computing. So really appreciate your comments and insight, and what phenomenal tests too. I mean, just the results there speak for themselves. And as Wayne said, the ask stack and these concepts apply to a multitude of use cases. But as we, if we bring the presentation back full circle to the use case challenges that we started off with, the oil platform can process and analyze data by leveraging on-platform edge data centers, ostensibly running on Snowball, where Couchbase is installed and syncs data to Capella in the cloud via Starlink. This keeps apps available and fast for the platform operators, which can serve to increase productivity and reduce safety risks. And I think right now we'd all love to see increased productivity in oil and gas to help bring down some of these crazy prices. And for those in-flight airline apps, thanks to in-cabin data processing and storage, the crew gets immediate access to passenger profiles and preferences. They can make engage in a highly personalized fashion. And meals and amenities and duty-free items are never oversold. And this, these simple things help make the customer's experience as personalized and comfortable as possible. which leads to loyalty and repeat business for the airlines. And for cruise lines, the ask stack and these concepts can provide the means for capturing and this constantly changing guest data while at sea, and using it for real time, in real time for offers and recommendations. It can lead to better guest engagement, and that all important upsell opportunity that can really grow the top line. So we also wanted to make sure that everybody in attendance today understands it. AWS Snowball is not the only AWS Edge service that we've worked with and tested. So we've proven out edge computing architectures with Couchbase, leveraging other emerging edge services from AWS, including local zones, outposts, wavelength, where similar tests really showed amazing reductions in latency for app reads and writes. These services make it easy for customers to spin up edge infrastructure for nearly any use case, because these customers can get AWS, that infrastructure in their local city, or on a 5G network, or on-prem, or even in extremely remote areas on Snowball, as we've seen. And because of our partnership with AWS, it really makes it easy for anyone to get started with Couchbase and edge computing really quickly. So, in summary, Couchbase Capella really does, fulfill that promise, or those promises of edge computing. It enables the ability to bring data and compute close to the point of interaction, where the data happens, right? Including onto the device itself. And all of this serves to decrease latency and insulate applications. It makes them impervious, if you will, from internet outages and slowness. And as Wayne's tests really proved out, Couchbase at the Edge provides the highest guarantees of speed, reliability, privacy, and efficient bandwidth use for applications. So as we transition into Q&A, want to make sure that everybody also takes advantage of the Couchbase Capella free trial. Go to cloud.couchbase.com and sign up. You can get access to the database as a service and those app services for synchronization, authorization, and authentication for Edge apps. So as we dive into some Q&A, I think we've got some questions coming in. Wayne, I'll ask the first one here. And maybe you can provide some of your insights here. How does the sync service handle things like conflicts? And that makes a lot of sense in a multi-client, environment. Can you tell our listeners how we handle that?
Yeah, sure. So conflicts are a common problem with eventually consistent systems. It's actually one of the fundamental problems. So you have changes happening in multiple parts of the system, and they're not able to communicate with each other because they're partitioned or have no internet connection between, or no network connection between them. So when and you write in both locations. Well, when you write in both locations at when they're offline, what happens when you try to sync? That's called a conflict. Right. So there's a conflict. What am I supposed to do during a write? So the Couchbase sync technology has automatic conflict resolution that is similar to last write wins. Right. It's really, in a tie situation, will be most active writer wins. But so we're going to choose the one that was the last one to be written. Right. So that's automatic conflict resolution. It works in most cases. Like most cases, you want something that converges. Right. This is the key component of conflict resolution. So we have automatic conflict resolution. Then we have custom conflict resolution that you can integrate on with our embedded database, right? So when you're running synchronizations from the client side, you can set up a custom conflict resolver in the native code and resolve the conflicts during sync. You're given the old and new document and some other information, and you choose how you would like it to be written. And then we also have the same in-sync gateway. So when you're replicating between gateway components, you can set up custom conflict resolution as you would like. So you have automatic conflict resolution, which is really great. And then you have custom conflict resolution that enables you to write whatever strategy you need for resolving those simultaneous writes.
And I think that customization is a big differentiator, right? From there are a few sync solutions out there, alternative sync solutions, but this really is one of the areas where we're set apart amongst other things. So,
yeah, it's needed in more complex systems, right? Like when you're doing business cases, right? How you, like I said, most conflict resolution automatic is fine, right? Product catalog items, right? Things like that. But when you're talking about more complex cases, being able to choose how things are resolved is important. And so we have that as part of the entire platform.
Great. A couple other questions coming in here. Gabriel is asking how the initialization process of replication is done.
Okay, so you configure replication in the app services or in the gateway when you're talking about replicating between two gateway components or app services in a gateway. And so in the test setup, what we had was in the gateway running on the Snowball. You really, in almost all cases, you want your replicator, the thing that's being the active participant in replication, to be the lowest in the stack of your network topology. That means that when it fails, that it only has an impact on everything below it in the stack or itself, if you're talking about the device, right? So in the test setup, the gateway running on the Snowball had a configuration for the replication, which takes the endpoint for the app services running in Capella, and then the username and password that the Snowball gateway is going to use when replicating with Capella. So that's secure replication, right? So that means you need to have an identity, and then that allows us to also only synchronize the data that we want to go to that location, right? So a big part of our synchronization technology, I know you didn't ask this, but it is an important point, is that you can control very fine grain what data moves to different parts of the system. So if you're in a case like a ship, for example, you might move all of your baggage data for a ship voyage onto a ship when it's on a specific voyage, right? So it might be like the Atlantic of the Seas, voyage 5, put the bags on onto the ship, right? The bag documents, right, or records. And then, so that's how, so you set it up in the gateways. And then as far as on the embedded device side, there's the same exact concept for embedded database. So you create a replicator object, set up the URL for the endpoint, or other types of endpoints, right? For peer-to-peer, there's a lot more options on the embedded side. And the username and password, and it syncs exactly the same way. So you can set up replicators in the embedded database or replicators at the gateway side. You're muted, Mark. While you're coming off, I will say also that you can have more than one replicator. That's also an important part, flexibility component that we have in our stack, is that you can have, you don't have to just think one replicator, right? Because of the way you're filtering and what you're pulling data from could be more than one component in the system. Replicators aren't, both in the embedded database and in the gateway, can be 0 or more, right? So you can have a lot if you would like.
Lots of precision, and that's really key. Thank you. Hopefully that answers that question for Gabriel. Gabriel asks another question. I'll see if the question specifically is, does Couchbase use snapshots of the database to the subscribers as SQL Server has in their replication mechanism? And I think this might be talking about perhaps a pre-built database or synchronous. Any thoughts kind of around this?
So we don't use snapshots, we use sequence numbers. So everything inside of each of whether you're talking about the entire database server, if you're talking about Couchbase Server or Couchbase Lite, as you make writes inside the database, each write is assigned a monotonically increasing sequence number. That's a point in time, right? So a logical point in time. And so when a device connects to replicate, they say, I'd like to replicate since, and then they have the last sequence number that they successfully synchronized and persisted, right? The different parts of the components have to have to handle this concept of where I am in time very precisely, right? You don't want any gaps in the continuity between thinking where you are and in time and where you actually are in time. And so they'll know where they've confidently stored a piece of data at this point in time. That sequence number is managed. You'll never interact with this concept, right? I'm just kind of explaining under the covers here, right? This is all just done for you, right? When you create a replicator, it knows what sequence number it's on because it's maintaining all of that accounting information, right? And so that's how we do it. And so when you connect, when a replicator connects to an endpoint, it says since 100 or whatever, and then we just replicate what they're able to see, what has changed since the last time they saw us, and 100 since 100. So you might go from 100 sequence 100 to 110 or something like that. It's a very efficient process.
Awesome. Thank you for that. Steve asks, this is a good one. Wayne, what are your thoughts on what kinds of compute power would be used at the edge? Do you need a high CPU count? Is what Steve asks.
I mean, Snowball is great, right? The edge computing services from Amazon, I don't actually know a vendor that has more solutions right now. There are other solutions out there, but Amazon's ability to go all the way to the edge, and especially the addition from their Snow family, is really great. So Snowball is awesome. It has massive amounts of compute and storage and memory, right? They have multiple versions of that. And then if you want to get a little bit smaller, right? The Snow Cone, which is the size of so the Snowball is the size of a suitcase, like this big. Right? Maybe can't even really show here, but yeah, about as wide as a screen. And then the Snow Cone is the size of a tissue box, so it's about this big. Right? It's still very, very capable. Imagine how capable your phone is, right? And then this thing is like slightly bigger than that, like maybe like 20 phones. So both of those are great options for near edge deployments. You could also deploy your own, right? Raspberry Pis are very common to deploy near edge, right? When you're talking about just a few things or smaller compute heavy systems are going to be used. And there's like a long tail of embedded systems that you can just buy, right? I like the pay-as-you-go model from AWS, and I imagine that the pay-as-you-go model for these types of compute will become more and more prevalent as we move forward. So that's near edge, and then on edge, right? And I guess you could use Raspberry Pi there, but the most common ones we see are phones and tablets and desktops, and really those come from 3 major vendors, right? So it's coming from Apple. Well, at least the OSs come from Apple, Android, Google for Android, and then Microsoft. And
right.
So those will be your devices that you're choosing for the edge.
So thank you for that, Wayne. On the point that Steve asked about needing a high CPU count, Couchbase Lite is the answer there for resource constrained devices. So the answer is that you can leverage kind of whatever CPU processing that your device can bring to the table. So,
and in our deployment, we deployed server and gateway on the embedded system. You could the Snowball, right? But as Mark is pointing out, you can deploy our embedded database on the device itself, like phones and things like that. But you could even deploy the embedded database on your near edge device, like a Raspberry Pi or BeagleBone or something like that.
Yeah, the options are really vast. And this is what is so exciting, is that we continue to find out how we can support the most complex edge topologies. And again, sets us really light years, leapfrogs us past any of the alternatives that are out there. So
you can deploy Couchbase. Let me just jump on that just a little bit. Is that
please.
Couchbase? That's an important point that Mark just made. Is that I pointed this out before, right? You need compute, networking, and a database, right? And so what Mark's pointing out is at the database level, this is fundamental, right? Underneath all of your applications is a database, and a database that can be deployed in an edge computing environment. You can't accidentally build a database like that, right? They have very special requirements, and the Couchbase database platform can be deployed from very, very large systems in the cloud down to smaller but still very capable devices near edge, and directly on devices, whether they're, have heavy compute and memory like our phones, or even smaller, less or more constrained devices like custom embedded medical equipment, is something that's common in our customer base.
Great. I think we only have time for a couple more questions here. Circle back to Steve, who asked another question. Can other compression engines be used? I believe he's, of course, referring to synchronization. Or is what's in Couchbase, the way to go, the only way to do it?
I mean, we do it for you. We don't allow plugging it in. I can imagine maybe you could do some tricks at the networking level, if you wanted to say disable it, run length compression inside of gateway, and do some tricks at the networking level because you want to compress as it enters, decompress as it enters your network or something like that. But we don't allow any type of compression plugins inside of our system at this point in time.
Got it. Well, but that takes onus off of the customer to have to do it. Leave the driving to us. Ostensibly makes the whole process a little easier. And yeah, sorry, do you had another point?
It's complicated. We get to make more. I could see why you might have your, a special case where you wanted to bring in compression, but we do more than just kind of dumbly compress things, right? Like we make a lot of choices. Like, is this thing even compressible? Where it would be a good trade-off between using my CPU to do the compression versus just transferring it over the network as it is. So and other systems do that too, right? But when it comes to compression, kind of leaving it to us is kind of the easy approach, and we do a great job of it, and we enhance this all the time, right? So we look at this problem a lot. We look at even how we batch our WebSocket. So when we replicate, we replicate over WebSocket. So how we even batch the messaging in that is we pay a lot of attention to that.
Sure. Lots of efficiency brought to the table there. So let's answer one more question and then turn it back over to Suzanne and wrap things up here. So what AWS Edge services are you validated on? Raj asks, and I'll take a stab at answering this and ask for any color commentary, Wayne, because I happen to know that we're service ready for AWS Outposts. We have reference architectures in place for local zones and wavelength. So reference architecture means, of course, that we've proven out the architecture. And latency testing has been conducted on local zones and wavelength specifically, similar to part of the test that Wayne did on Starlink and Snowball. And Wayne, I'll just throw it out there. Do you think, is Snowmobile next, or who knows? We can just keep riding the train. We just keep proving the value. So I'd love to have a snowmobile dropped in the Couchbase parking lot and test that out. Who knows?
Yeah. Snowmobile is fun. It's a semi. If you don't know what that is, so the Snow family has Snow Cone, which is like the size of a tissue box. Snowball, that's a suitcase, and then Snow Cone, which is a semi. The Snow Cone, Snowmobile is more for storage. So if they end up adding a ton of compute, or you could drop one of these in next to a factory or something like that, I imagine it would be something we could add a lot of value to. But for now, it's mostly Snowmobile is mostly for transfer of data to the cloud, large transfers of data to the cloud. But I will just point out that the way Couchbase is architected is to run in any network topology. So we touched on a number about any network configuration that you can think of, right? So these are the first principles that we focus on, right? Like, how can we enable all of the types of architectures that you all may need? And then, of course, validating on as many cloud services as we can as they come out, right? These are all new services that have just come on the market in just the last few years. So anyway, that's as much as I'll add there.
Great stuff, though. Always so fun. we thought we were going to only do about 30 minutes, and we're at the top of the hour. So that's how in-depth this conversation has been, and I think it's been fascinating. Hopefully all of you in attendance agree today. I want to thank Wayne for being our subject matter expert today, running those tests, and just being a wealth of great wisdom and information. Thanks for your insights. Thanks, Suzanne, for putting all of this together.
Yeah.
And again, Mark from Couchbase, and appreciate everybody in attendance. And take a look at all of these resources that Suzanne has assembled for you. We've got a write-up, the paper actually behind the Ask Stack tests, and other things of how Couchbase actually supports edge computing. So with that, thanks everyone for being here, and hope you have a great day.
Take care.
Thank you.